Okay, seventh question. This is easy one except for a small trick there. So this is a charging process and you have a battery charger and its EMF is 14 volts. So EMF means energy converted from other forms to electrical forms. It is not just in the context of a battery where the energy is converted from chemical. It could be from your main electricity board where the energy is being converted from petroleum, which is also chemical, but also from waterfalls potential energy. So EMF is something that describes any uh, conversion from other forms to electrical. So the charger has an EMF, this 14 volts. It has a internal resistance 0.1 ohms. So internal resistance is again a resistance in the mechanism of the source. Yes, for a battery it has to overcome the chemical bondings. In case of the, let's say, a transformer, it has to overcome the resistance in the transformer circuit. That is its internal resistance, but whatever. So EMF and internal resistance, these two are something common. So you have 14 volts, 0.1 ohms, and you have the battery of EMF E and 0.06 ohms. They are connected, and they are asking you to first find the total resistance. That's no issue. You have 0.1 ohm and 0.06 ohm, so the total resistance is 0.16 ohms. Now they are asking you to drive the total EMF in the circuit. So you go around the circuit. So you start here, then you go here, then you start moving this way, you come here down. So if you complete a circle like that, there are only two EMFs that are there. One is this 14 volts, the other is this E. And if you look at them, the plus of this one and the plus terminal of this one are connected, and the negative of this one and negative of this one are connected. So it is like two batteries opposing each other. So the resultant EMF would be the difference of them. So it should be 14 minus E logically, because then only the current will flow from the positive terminal through the positive terminal to the negative terminal of the battery. Because when the battery is normally functioning, that is while it is discharging, while it is supplying energy to a component, the current goes from plus to minus. So while it is being charged, the current should go the other way around. It should go from minus to plus. So if the current should go from minus to plus in this battery, that means the current should go from the plus terminal of the source to the negative terminal of the charger source. So that means this voltage should be greater than that one, so 14 minus E. But you can at this moment you can write it either way. But when you're going to apply the V is equal to IR in the next question, you need to be careful if you are writing it the other way. If you're writing it E minus 14, then you have to give minus for the current direction. It might confuse you when you're talking about direction for the current, because current is not a vector. But what we mean by the direction is the current should actually go from in this circuit, the current should actually go clockwise, right? Then only the battery will get charged up. It should go like this. But if you have taken the EMF of the circuit as E minus 14, saying that E is greater, that means you are saying that the current is going anti-clockwise. That's not possible. The current should go clockwise. So when you are applying the equation V is equal to IR, if you have taken the resultant EMF as E minus 14, then the I value should be given a negative sign indicate, because according to you E minus 14 means that the current should be anti-clockwise, but the current should actually be clockwise. So when you're applying V is equal to IR, you should give a negative sign to the current. But that something like practically very confusing, like when you're talking about negative sign for the current. So it's rather we go with the logic that if it is getting charged, that means sorry, if it is getting charged, that means the charger the current should go from the positive to the negative terminal of the battery. Sorry, negative to the positive terminal of the battery. It should go the other way than the usual. So it should be clockwise. So the 14 volts should be greater than the EMF. So that is what's asked in the second part. You are applying the V is equal to IR to the circuit of Kirchhoff's second law to find the EMF of the battery. The mark scheme accepts both, but the second method has, like, it's correct in its application, but it's not very logical. So you can see here, so you can go either 14 minus E or E minus 14, but if you're going E minus 14, you have to give a negative for the current. But if you're going 14 minus E, sticking to the logic, then that's easier. Okay. Well, speaking strictly, you're not giving actually a negative for the current, you're actually giving a negative for the potential difference. For convenience of application, we say we are giving negative value for the current, but strictly speaking, actually it is the negative value for the potential drop across the two resistors, right? Implying that the battery is getting charged. Okay, but this is easier and more logical.